October, 1973. The Sinai Desert is ablaze. Israeli tanks are counterattacking, confident in their armor. But within minutes, they're burning. They're being destroyed by infantry. This is a revolution on the battlefield. For the first time in history, entire tank columns were stopped, not by other tanks, not by bombers, but by ordinary soldiers with missiles. Thus began a new era of warfare. The era of the anti-tank guided missile. If you're interested in the technologies that changed the face of modern warfare, give this video a like and subscribe for more deep dive content. Today we will examine how this high-tech hunter is designed. An ATGM consists of 4 key components: rocket engine, warhead, guidance system, and missile control surfaces. These elements may be arranged differently within the missile, but all of them are present in every ATGM. Let's examine each component in detail. A solid propellant rocket engine is usually used as the propulsion system. Often, a special powder charge is additionally employed to push the missile forward a few meters out of the transport launch container, after which the rocket engine ignites at a distance. This is done to protect the ATGM operator and the sensitive electronics from the flame and hot gases of the operating engine. The flight speed depends on the specific missile and usually ranges from about 100 meters per second to 600 meters per second. Some missiles can accelerate to speeds exceeding 1,000 meters per second. The missile's range for man-portable systems is typically between 2 and 5 kilometers. Missiles designed for launch from ground vehicles or helicopters can reach up to 25 kilometers. The warhead of an ATGM is usually a shaped charge, whose explosion forms an aerojet of metal that effectively washes out the armor at the point of impact, due to the high pressure of the hot metal focused on that spot. Since modern tanks are often protected by reactive armor, tandem warheads are used to overcome it. These are essentially 2 shaped charges, placed one behind the other at a specific distance. The first, smaller charge triggers the reactive armor, while the second, larger charge penetrates the main armor. To engage infantry and destroy fortifications, thermobaric warheads are used. Upon impact, they disperse a special aerosol which is then ignited. High explosive warheads can also be used against infantry. There are also specialized types of warheads, such as kinetic warheads, which penetrate armor through the missile's high-velocity high-explosive armor-piercing warheads, which destroy armor from the inside by detonating on its surface, and warheads with special blades designed to eliminate terrorists with minimal harm to nearby civilians. Which type of warhead do you think is the most effective on today's battlefield? Let us know in the comments. Guidance systems are the primary factor by which ATGMs can be conventionally divided into 3 generations. The first generation requires the operator to manually guide the missile. This is known as MCLOS, Manual Command to Line of Sight Guidance. The second generation only requires the operator to keep the crosshairs on the target until impact. This is SACLOS, Semi-Automatic Command to Line of Sight Guidance. The third generation requires the operator to lock onto the target and launch the missile, after which it flies and guides itself. Let's examine each missile guidance method in more detail. MCLOS guidance. The operator observes the missile's tracer and controls it manually using a joystick. The missile receives control commands through wires trailing behind it. This control system is technically simple but highly dependent on the operator's skill, and thus has low accuracy against fast-moving targets. It also has a short range limited by the wire length, and control can be lost if the wire is broken. Examples of such missiles include the Soviet Malatka, the French SS-10 and SS-11, and the Swiss Cobra. SACLOS wire-guided guidance. The operator keeps the sight crosshairs on the target, while the system tracks the missile. usually via an infrared flare on its tail, and automatically sends correction commands through wires trailing behind the missile. This system is less dependent on the operator's skill and is capable of hitting fast-moving targets. The missile range is limited by the length of the wires. Guidance may be lost due to wire breakage or interference with the missile tracking system, such as infrared countermeasures. Examples include the American Twin Dragon, the Russian Fagot, Concourse, and Metis, the Franco-German Milan and Hot, and the Chinese HJ-8. SACLOS radio-guided guidance. This guidance method works similarly to the previous variant, but instead of wires, the control commands are transmitted via radio. The main advantages are increased flight range and independence from wire limitations. However, the issues related to infrared countermeasures used to deceive the missile tracking system still remain, and new vulnerabilities to electronic warfare interference are introduced. Examples of ATGMs: the Soviet Cobra, the Russian Shturm, and experimental versions of the American TOW. SACLOS guidance using a laser beam riding method. As in previous cases, the operator simply keeps the sight aimed at the target. The sighting system directs the laser beam at the target. After launch, the missile enters the laser beam and begins to ride it. From that moment, the missile attempts to stay within the laser beam, while the sighting station keeps the beam on the target. Signal sensors in the missile's tail section compare signal strength from various points on the missile's body and use this data to generate control signals that steer the missile toward the center of the beam. This system is widely used for guiding ATGMs fired from tank guns. It eliminates the drawbacks of the previously discussed systems, as the missile essentially guides itself using the laser beam. However, there is one nuance. Continuous laser illumination of the target is required, which means the target may detect the guidance using special sensors. Additionally, weather conditions such as rain, fog, or smoke can lead to loss of missile control. Examples: Ukrainian Stugna, Russian Reflex, Vikram, Kornet, American Lozet and Adits, and Israeli Matpots. SACLOS guidance using a radio beam riding method. This method is similar to the previous system, but instead of a laser beam, a radio beam is used. The use of a radio beam allows missile guidance in poor weather conditions, and optical systems on the target cannot detect the illumination. However, this guidance system is susceptible to electronic warfare interference. Example: the Russian Chrysanthema, Inertial guidance system. The operator tracks the target through the sight for a short time, then launches the missile. The system, based on gyroscopes and accelerometers, receives the target's distance, speed, and initial position at launch and guides the missile toward the predicted location where the target will be. The main drawback of the system is that if the target changes direction or speed during the missile's flight, the missile will miss, as it does not receive updated target information. This system is typically used in combination with other guidance methods that can make in-flight corrections, but there are ATGMs based solely on this guidance system. Example missile: the Swedish-British law SACLOS guidance using reflected laser radiation. As in the previous method, the operator keeps the sight aimed at the target, and the sighting station illuminates the target with a laser beam. However, in this case, the missile has a laser sensor in its nose, not in the tail, and it orients itself by detecting laser radiation reflected from the target rather than riding the beam. Such missiles often include an inertial guidance system as well. This allows the sighting system and the launch platform to be separated by a considerable distance. For example, a helicopter can launch a missile and then leave the area, while ground troops illuminate the target with a laser. The problems of this guidance method: targets can detect that they are being targeted, and weather conditions such as fog, rain, or smoke can interfere with guidance. Examples of missiles: the American Hellfire, Maverick, ATGM, the British Brimstone, and the Israeli Warhead. Guidance using an optical homing head, the operator, using either a sighting station or the optical seeker in the missile, essentially a camera, locates and locks onto the target before launch. After launch, the missile continually compares the current image of the target from the seeker with earlier frames, tracks the target's movement, and generates control signals to steer the missile. This guidance system allows the operator to leave the launch area immediately after firing. Drawbacks of this system include the requirement for the target to have sufficient visual contrast with its background for stable tracking, and significant sensitivity to weather conditions such as smoke, fog, rain, or snow. Additionally, it is nearly impossible to lock onto targets at night without infrared capability. Examples of missiles: the Israeli Spike, the French ATGM, and the American Maverick. Guidance using a thermal imaging seeker head. This works on the same principle as the optical seeker head, but instead uses a thermal imaging camera. The main drawback of this method is that if the target's temperature is not higher than the surrounding environment, it becomes impossible to lock on. For this reason, this method is often combined with others. Examples: the Israeli Spike missile family, the French ATGM, the American Javelin, Maverick, ATGM, and the Chinese HJ-12. Television guidance. The operator launches the missile, which has an optical camera in its nose. The image from the camera is transmitted via wires or radio to the control station, where the operator uses control systems to guide the missile to the target. Control signals are transmitted by wire or radio as well. This guidance method is usually combined with optical or thermal homing guidance, allowing the operator to manually guide the missile only in the early flight phase and switch to autonomous terminal guidance by the seeker head. Examples of missiles: Israeli Spike, French ATGM. Guidance using a radar seeker head. This method operates on a similar principle to optical and thermal seeker heads, but while those only receive electromagnetic waves in the visible or infrared spectrum, the radar seeker head actively emits radio waves and receives their reflections from the target. Using radar enables guidance that is not dependent on weather conditions and allows the tracking of cold or visually camouflaged targets. However, this guidance system is vulnerable to electronic warfare. It is often used in combination with other guidance types. Examples of missiles: American Longbow Hellfire, ATGM, and British Brimstone. Missile control surfaces consist of wings and control fins. Depending on the design of a specific missile and its guidance system, these elements can follow a conventional layout, with wings at the front and fins at the rear, or a canard configuration, where the fins are in front and the wings are in the rear. The wings provide aerodynamic stabilization and lift, which increases flight range and helps maintain maneuverability. Control fins adjust the missile's flight path, pitch, and roll based on commands from the guidance system. Some ATGMs spin in flight due to design features related to stabilization and targeting used in specific missile systems. If you've made it this far, you're clearly passionate about military tech. Like the video and subscribe to support the channel. It helps us bring you more content like this. An anti-tank guided missile is not just a projectile, it is the result of decades of engineering evolution.